Welcome to Calc Chats 22. Today we're going to be talking about anti-differentiation using U-substitution. U-substitution is kind of our integral equivalent of the chain rule. So we need to use it when we have composite functions. So for example, if I wanted to take the derivative of, that's a d, oh my goodness, the derivative dx of e to the cosine x, I would need to take the derivative of e to the cosine x, which is just e to the cosine x, times the derivative of cosine x, which is negative sine x. So we use this U-substitution when we have two functions that are kind of related to each other. So our first integral looks familiar. So I want to evaluate this integral. So just as we saw when we were taking the derivative, we had this kind of inner function cosine, and we had its derivative sine. And so we call the inner function u, and its derivative is du. Sorry, this should be negative. Negative sign. So as long as I can find the u and the du in my original integral, I know that I have picked kind of the right ones. And so when I set up this integral, I want to set up in the form something that looks like u times du. In this case, it'll be e to the u times du. So I want to set up my integral e to the cosine x times du, negative sine x dx. So if I look at my original integrand, this does not have a negative attached with it. And so in order to make my du negative, I need to multiply my outside by a negative. So it'd be the same thing, multiplying this by a negative, so negative du, that gets me a positive sine x, which is what I want. So now I can rewrite this this integrand in terms of u and du. So I rewrite this as negative e to the u du, and I can integrate that. And so the integral of negative e to the u, or the negative integral of e to the u du, is just negative e to the u plus c, and then all I do is sub back in whatever is my u. So since cosine was my u, I sub that back in, and I get that antiderivative. Our second function that we're going to be looking at is x squared times square root of 5 plus 2x cubed dx. And so if I look at this outside part, x squared, I kind of see, okay, that could be the derivative of 2x cubed. And so I pick my u to be the inside, so 5 plus 2x cubed, and my du is going to be the derivative of this. So I take 6x squared dx. So now in order for me to get things in terms of my u and du, I noticed that in my original, I'm missing that 6. So what I need to do is I need to multiply my du by 1/6. So this ends up looking like 1/6 times 5 plus 2x cubed times 6x squared dx. Because this is all, again, this is all my du, but if I multiply by 6, this becomes 1, and I end up with my original. So I need to kind of balance it on both sides. This is just basic algebra when you make sure that you kind of are balancing out the scale. So now I can write this in terms of u. So I'm going to write this as u to the 1/2. That's just going to make it a little bit easier to integrate. So 1/6 times u to the 3/2 over 3/2 plus c equals 1/6 times 2 over 3 u to the 3/2 plus c. Again, this is all just algebra here, and then this becomes just 1/9 u to the 3/2 plus c. Plug back in my u, 5 plus 2x cubed to the 3/2 plus c. So here's your DIY problem, the integral of cotangent 7x dx. And so my first piece of advice for you would be to split this up in terms of cosine and sine. So go ahead, if you want to do it yourself, copy this down and try to solve it. So here is my work. First I split it up into cosine and sine, and from there that helped me kind of better see my u and my du. So you should get 1/7 ln, the absolute value of sine of x plus c. So when we're dealing with definite integrals and U-substitution, we have to do a little bit of maneuvering with our bounds. So this first example, we're trying to evaluate the integral from 0 to pi over 3 of tan x secant squared x dx. And so I kind of already gave you a hint, let u equal tan x and du equal secant squared x dx. And so there's two ways to kind of do it. I'm going to write this first way in green. This is not changing bounds, and this is kind of doing a little bit of illegal math. Not too much though, so it's okay. It's just like jaywalking. So first of all, what I'm first going to do when I don't change my bounds is I'm just going to, once I have my u and du, I'm just going to put it in terms of that. So u and du, I'm just going to solve this like a definite integral, and so I get that this integral is u squared over 2. Then I'm going to change it back into terms of u. So this becomes tan x squared over 2. Now I can keep the bounds 0 to pi over 3. So then I plug in tan of pi over 3 squared over 2 minus tan of 0 squared over 2. Tan of pi over 3 is the square root of 3, not cubed, squared, over 2 minus 0 squared over 2, so this ends up being 3/2. So that's one way, is to just integrate or take the antiderivative and then use the bounds. The second way is kind of the same idea, except we're just changing the bounds in the beginning. So this is changing bounds. So what we're going to do is, first thing I'm going to take is I'm going to find u of pi over 3. So u is tangent, so I'm going to find tangent of pi over 3, and that is root 3. And then I'm going to find u of 0, which is tangent of 0, which is 0. So then when I take my integral of u du, my bounds change from 0 to root 3. So this becomes u squared over 2 from 0 to root 3. Then I get root 3 squared over 2 minus 0 squared over 2. So I still end up with the same thing. It's just a slightly different method of how to get there. So this is Calc Test 22. This is U-Substitution. Please make sure to come to class with any questions you may have, and like and subscribe.